A confidence interval corresponds to a two-sided hypothesis test. It provides an interval estimate for a parameter. We can use our sample to construct this interval, and we'll have some level of confidence that the interval contains the parameter. It's not that difficult to derive a confidence interval for the mean using the central limit theorem. Recall that the standard normal distribution has mean 0 and standard deviation 1. If I draw a random number from a standard normal distribution, there's a 95% probability that it will be between negative 1.96 and 1.96. You see, 2.5% of the area is behind negative 1.96, and 2.5% is ahead of 1.96. So the middle 95% of the distribution is between these two numbers. If you were doing a two-sided hypothesis test at the 0.05 significance level, this is the area you wouldn't reject. We're talking about a standard normal distribution here. Mean is 0, standard deviation is 1. Recall that any random variable that follows a normal distribution can be standardized. If x follows a normal distribution with mean mu and standard deviation sigma, then x minus mu divided by sigma follows a standard normal distribution. The central limit theorem says that the sample mean has this normal distribution. So if you take the sample mean, subtract mu, and divide by sigma divided by the square root of n, then you have something that follows a standard normal distribution. The probability that this thing is between negative 1.96 and 1.96 is 0.95. And that's what I've written here. Now, I want to get this mu by itself. Let's look at the first half of this inequality. I can multiply both sides by this denominator, sigma divided by the square root of n. I have sigma and square root n are both always positive, so I don't have to worry about this inequality sign getting flipped. If the denominator could be negative, that would be an issue. But now, if I subtract the sample mean from both sides, and now to make mu positive, I multiply both sides by -1, and that does flip the inequality sign. Remember, whenever you multiply by a negative, the inequality sign flips. 2 is less than or equal to 3, but -2 is greater than or equal to -3. And we have mu less than or equal to I'll do the other side as well. And now multiplying both sides by -1 and flipping the inequality, Putting these two inequalities together, we now have this. What this means is that if you take a sample, the probability that this interval contains mu is 95%. And we need to be careful about how we think of this, because remember, mu is not random, so there's no probability associated with it. What's random is the sample mean, and that means these bounds are random. We're talking about the probability that these bounds surround mu, not the probability that mu lands between these bounds. It is considered incorrect to say that a confidence interval has a 95% probability of containing the parameter. But as you can see, it is a probability statement. It's just that you have to be clear about what's random and what's not. The standard way to interpret a confidence interval is to just avoid the mention of probability altogether and say that we are 95% confident that the population parameter is between the lower bound and the upper bound. And as we've seen, this interval was developed out of a two-sided hypothesis test. You can actually use a confidence interval to perform a two-sided hypothesis test. Construct the interval. If your hypothesized parameter mu is in the interval, you fail to reject the null hypothesis. If it's outside the interval, you reject the null hypothesis. Here's how to construct a confidence interval using the electric company example. The sample mean is 1025, and that's going to be the center of the interval. And I'll put plus and minus. We have 1.96 for a 95% interval, and that comes from the standard normal distribution. Multiply that by sigma, which is 100, and divide by the square root of n, which is the square root of 50. We are 95% confident that the population mean is between these two numbers. The numbers turn out to be 997.28 and 1052.72. We are 95% confident that the population mean energy consumption for single-family homes in this area is between 997.28 kilowatt hours and 1052.72 kilowatt hours. Our null hypothesis was that mu equals 1000. Since 1000 is within the interval, we would fail to reject the null hypothesis at the 0.05 level. And that's the same result we got from the p-value approach.